Hello, my name is Subhi Barg. I am an assistant professor at Mead Sweden University. My presentation of today is entitled Wrong Air Gap Calculation Formulas. So today I'm going to discuss some of the existing expressions that are used to calculate the air gap. I'm going to show why they are wrong, and I am going to also to propose or to give you a new uh, formula that can be used, the exact formula that you should use for the calculation of your air gap. So as I have said, there are different expressions to calculate the air gap. And among these expressions, I have chosen these two, which I have found written in most of the books and the technical documents of the vendors of magnetics. And these expressions, the first expression, it is a function of these variables, as you can see there. So the first expression, the air gap, it is proportional to the inductance, and it is inversely proportional to the cross sections. Minus the second term, which is the ratio between the magnetic core length and the relative permeability of your magnetic material. And this can be neglected if the permeability or the relative permeability is very high, and that's the case for the ferrite material. But for other materials, so you need to consider this term. The second expression, before that, the first expression, it is derived, just to mention, it is derived from equating the energy, Li square, and that's the energy stored in the inductance, and you equate it to the energy, the magnetic energy, which can be written as function of the reluctance and the flux square. So this is from where you can derive the first expression. The second expression, it is derived from the reluctance model of the inductance, and as you can see, it is proportional to the n square and the cross section divided by the inductance, and minus the same term as the first expression. So both equations, they are wrong, and the simple answer, or the simple reason why they are wrong, is because the air gap, it is independent on the cross section of your magnetic core. That's the common mistake that most of the engineer and also professor, as I have seen in most of the lectures, you can find it online. They use to consider the cross section as a variable that's the air gap depends on, and that's not correct. The air gap does not depend never on the cross section, and I will show you why it's not depending on the cross section. Of course, I will in the first step, I will show this by intuition, and in second step, I will give you the correct and the exact equation to calculate the required air gap for your magnetic core. So to understand why the air gap is not depending on the cross section, there are several ways to prove this. The first approach is by intuition. So we can consider the following example. Suppose that you have designed your inductor. You have selected your magnetic core that has a specific magnetic length, and you have selected the number of turns and so on. And you have also calculated the required air gap. And then you need to change the design because the magnetic flux density, it increases due to an increase of the current. You are changing the application, or you have changing the excitation voltage. So what you are going to do in that case, so one solution for that you could choose is to, which I don't prefer always, is to increase the cross section. But I'm using it here just to explain why the air gap is not depending on the cross section. So increasing the cross section, what it will happen to the magnetic flux density, it will reduce to its original value. If you increase the cross section by a factor of x, the same factor that the air gap, the magnetic flux density, it will increase. So the magnetic flux density, it will reduce by a factor of x. And also from an energy perspective, the energy capability of the magnetic core, the magnetic material, it will increase also by a factor of X. The same thing what will happen to the gap, the energy capability of the gap, it will increase by the same factor because it is the same cross section here. So you don't need to change the air gap at all, because if you change the cross section, then your magnetic core, it will not saturate, it will be able to handle that energy, because the energy capability of the air gap, it will increase by a factor of X. The same thing for the magnetic core. So this is my intuition. In order also to explain why the air gap is not depending on the cross section, we can look to the expression of the inductance, the reluctance model of the inductance. So it is function of the cross section, the number of turns square, and the magnetic core length, the permeability, relative permeability, and the air gap. This is the main variables of the reluctance model of the inductance. Any change of every or any variable of this set of variables, it will change the inductance. This does not mean that the air gap, it is also function of the remaining variable plus the inductance. That's not correct. You can explain this if you have an equation y that depends on x and z, and this y, it is the function, it could be let's suppose it's function of h, and x, it is expressed as function, it has a function f, z also it has a function g. This does not mean that z, it is also a function h1 that depends on x and f and y. This is not correct. It is not necessarily correct that z should depend on x in this case. And it's in most of the cases also, it should not depend at all. So to correct the expression of the air gap in this case, so here the cross section, it is hidden in the equation or in the value of your inductance. So what you have to do, this equation is only correct if you relate the cross section to the value of your inductance. So you have to write it in a way that the inductance, it is calculated for that given cross section, and you cannot sweep the cross section. If you sweep the cross section, your inductance will sweep also. So, but in most of the optimization or the design cases that I have seen in the papers or in any technical documents, they fix the inductance from the beginning and then they change the cross section. So, but that's not correct, the correct way to optimize your inductor. So here another explanation how the inductance or how the air gap is not depending on the cross section. So the exact equation to calculate the air gap, it is given in front of you here. And as you can see, it is function of the number of turns, the DC current, and the second term is the ratio between LC and mu r, and it's divided for the first term. It is inversely proportional to the magnetic flux density. The magnetic flux density, it is up to the designer to fix that one. It could be the maximum magnetic flux density or the optimal operating B. It's up to the designer to fix this. So as you can see here, there is no cross section, and that's the correct equation to calculate your air gap. So now let's try to understand this equation and try to derive the main conclusions from this. So the first conclusion that we can understand is the uniqueness of the air gap. That's the most important and the fundamental point that every designer should understand about the air gap. There is only one unique solution of the air gap for a specific number of turns and a specific magnetic core length and specific relative permeability or magnetic material and a specific DC current. The B, magnetic flux density, it is an optimal, should be optimized, that one. And now how we can derive this expression, before I go to the second conclusion, is you can calculate the average power and you divide it by the frequency to get the energy or the electrical energy that it will be converted into magnetic energy also. And you can see the magnetic energy, it's the sum of the energy stored in the air gap and the energy in the core. So if you equate both, you can get that equation into lines. It's very simple. I'm not going to do it, but let's move now to talk again about the uniqueness of the solution of the air gap. So a unique solution of the air gap, it will give also a unique value of the inductance. There is no multiple choices of the inductance for a given magnetic core and a given number of turns. And this explain, if you look to any catalog of the vendor of magnetic components, you will see that they have different series of inductor there, and for every series they use the same core, the same number of turns. In few cases they change the number of turns, but in most cases they keep the same number of turns, and the DC current of that inductors of this inductor, those inductors, they are also the same, but you see different values of inductors. There are different inductance, multiple one. So as you can see here, all those inductors, they are weakly designed, because from this equation we understood only that there is only one unique air gap for that, and that will give also one unique inductance for a given magnetic core that has a given number of turns that will be used to handle a specific current. So the second point I thought I would like, before that, Professor Chuk, he talked about this point in his post in LinkedIn, and he called this the fake inductor. Yeah, that's true. I fully agree with his opinion on that. The most of the inductors that's sold now in the market, you find in the market, they are all wrong designed. So if you need to design a correct and non-fake inductor, so you have to satisfy this condition for the air gap. If you have to change the inductance, it's not the air gap that will change. You have to change the number of turns. That's the optimal approach. I'm not going to discuss this point because there is no time for that, but maybe in next videos I will discuss this point. The second point I would like to mention here, that from this equation you can know which material that requires air gap and which material does not require. So here, if you put the air gap equal to zero, then you can determine, or you can express the permeability as function of the number of turns, as you can see here in this figure. For a given current and a given magnetic core, you can express the relative permeability as function of the number of turns. And as you can see here, you will get the relative permeability. It is inversely proportional to the number of turns. It's 1 over x. It has the same form as the function of 1 over x. And you can see the evolution of the relative permeability. So the area that above in the top of this curve, the red curve, is the area for the materials that requires air gap. The area in the bottom to the curve is for the materials that does not require an air gap in your design, and that's for a given number of turns. So if you fix the current and you choose a magnetic core and you try to choose, okay, I will choose which material that requires air gap and those that does not require an air gap. So you can plot this one and you can determine, you can know which material that requires air gap and which not. So this is, I came up to the end of my presentation for today. I hope that you will find this one useful. I am open to any comment and feedback for this, for this presentation. So thank you very much for your attention.